All right, so like we were saying, today's class is going to be our final new day of volume material. And in many ways, it's the most interesting because it introduces a brand new kind of volume measurement. That is the measurement that in so-called cylindrical shells. But it also adds this interesting ambiguity in which when we look at new measurements of volume, or we look at new areas that we're trying to measure, we now have an actual choice ahead of us. Do we want to measure volume using the disk or washer method, or do we want to measure it using cylindrical shells? So not only do we learn a new method, but we also have to begin to think about which method is the best method to use in a given situation. And that's brand new for us. So let's see, where did we leave off? So in the video, we talked a little bit about the theory behind cylindrical shells, and it was enough for us to derive this formula right here. So as a reminder, if we take a region and revolve it in space, we'll end up, I won't even draw it. We end up getting a region that looks like this perhaps. Oh, I'll draw it a little bit. We end up, getting some sort of region here. That was a mistake to try to draw that. We end up getting some sort of three-dimensional region here, which we previously could approach by using the washer method. Washer instead of disk because we can stick our arm through it. But this time, we instead decided not to slice it into washers, but instead to slice it into these cylindrical shells. And so rather than integrating up the area of a washer, which was the area of the big circle minus the area of that smaller circle, or the area of the big disk minus the area of the smaller disk, instead we can integrate up the area of a cylinder. And the area of a cylinder was given by 2 pi times the radius of the cylinder times the height of the cylinder. And we can see this as we saw in the video. And I always love this. I think it's such a fun geometric, intuitive observation. If we have a cylinder, right, a cylinder like this piece of paper, we can figure out the surface area of this by taking 2 pi times the radius, that's just the circumference of the bottom, times the height of the top, because the circumference at the bottom becomes the bottom piece of this piece of paper, right? So this just becomes a length times width formula. So I absolutely love that. A great little visual geometric proof for the surface area of a cylinder. So what we end up integrating then is essentially the expression 2 pi times the radius of each cylinder times the height of each cylinder. And we interpreted that using an appropriate radius and using an appropriate height. Now, as we did in disks, right, with disks and washers, we have this formula here, but I prefer to keep it general. So under problem 2 here, I'm going to write what I think of as the most general formula, which involves the radius and height. So it's the integral from a to b. We have 2 pi times the radius at a given value times the height at a given value. And then the idea as we go forward is that we'll have to interpret what r of x is and what h of x is using some geometric intuition, using the definition of the function as we saw up above. So rather than memorize an explicit formula like this, the x minus L times f of x, I tend to dislike that personally, and I prefer to rederive it from this step right here. So just so you know, that's my approach to these, and that's how I will be sort of thinking about this. Let's start by going over an example, because even though we talked through the theory last time, we haven't explicitly worked through an example yet. So let's start with problem 2. I'm going to zoom in here so we've got some space to work. So consider the solid obtained by rotating the region bounded by these 4 curves about the y-axis. Calculate this volume using cylindrical shells. Let's give this a try. So first step, which we've come to expect at this point, is to draw a picture and figure out what that picture looks like. That will give us some intuition on how to go forward. So we've got several lines. We've got x equals 1. That's this line here. X equals 3. Going to be this line here. We've also got y equals 1, so that's this horizontal line. Y equals 1. And as I'm doing this, I realize I probably drew a poor picture, so don't copy me just yet. We've also got the curve y equals x squared, which is going to look like this. Shoot way up there. So let's rescale this picture. I'm just going to rescale it. I can actually leave those, I think. I'm going to rescale this just by putting the y equals 1 lower, perhaps where it belongs, down here. Okay, here we go. And so y equals x squared, that final curve is going to be something like this, a nice parabola. So the hope at the end of this is that we have this nice region here. And the hope is always that it's an unambiguous region, right? Going back to that conversation at the start of class, the hope is that it's clear what is the bounded region. And so hopefully it seems like it's this little region right here. So our goal is to revolve this region about the y-axis. We're going to revolve that around this curve right here. Okay, so this is our setup. If we were doing the disk method, right, or the washer method, what we would do is we would take a little cross-sectional slice that is perpendicular to the axis of rotation, so it's lying flat like this. And then if we took that slice and we revolved it, what we would get as a result is this sort of flat disc, or in this case, a flat washer, right? It would be perfectly flat. It would have this hole in the middle, and we'd end up with something that kind of looks like that, which we would then integrate up. But we are not doing the disc or washer method this time. Instead, we want to revolve a vertical line, right? A line that is parallel to the axis of rotation. So if it's parallel to the axis of rotation, and then we revolve it, we're going to get this cylindrical shell that's being created, right? And that's in contrast to if we turn it like this, that would give us a flat disc that's being created. Here we're going to create the cylindrical shell. So we take this line, we revolve it, and the end result is that we get this cylindrical shell that we will then integrate up across all of the different x values, right? So this was one particular x value, but we could also take any one of these other x values and similarly revolve them in the same manner. So because each cylinder is indexed according to its x value, right? This green one that we drew, it was sort of identified by its specific x value. Our integral is going to be an integral involving the variable x. So what we get here is that this integral becomes an integral as x goes from something to something, a bunch of functions, and then at the end, we're going to throw in a dx. Now, then the question becomes, what is this thing that we are integrating? Well, according to the formula, it's 2 pi. Well, maybe we should say it's x goes from its leftmost x value to its rightmost x value. So that's x equals 1 to x equals 3. And then we have 2 pi times, we need the radius of the corresponding cylinder defined as a function of x times the height of the cylinder defined as a function of x. So let's go back to our green picture and try to figure each of those out. First up is the radius at a given x value, like the one that we've identified here. The radius of this cylinder is going to be the length from the axis of rotation out to this x value right here. Right? In other words, the radius of this cylinder is going to be this length, which is equivalent to this length. And that length is just exactly equal to x, right? Notice it's going from x equals 0 up to x equals our chosen x value. So if we're looking, maybe to say that in slightly different words, if we're looking at a value x, such as this value right here, then the distance from the y-axis to that x value is exactly x. So maybe I'll just record that off to the side here. The radius of this cylinder is just equal to x. Now the height of the cylinder is going to be this height, you probably can't see that, this height right here, right, is going to be this height right here. And we can measure that at a given point x, that is going from this y value up top to this y value at the bottom. So the height is going to be given by the curve up top minus the curve at the bottom, or in this case, h of x is given by the curve up top is x squared, y equals x squared, and the curve at the bottom is equal to just y equals 1. So this distance, this physical vertical distance, is just x squared minus 1. And then our formula, we end up with 2 pi times the radius times x squared minus 1. And then we've set up our integral, and we're good to go. So this integral, when computed, will give us the actual volume. In general, and we've seen this now, this is a pattern that will continue. In general, I'm not going to ask you to explicitly calculate the volume. I want to, of course, point out that we can. In this case, we could factor out the 2 pi. We could distribute this x, right? We could, distribute everything out. So this would become x cubed minus x, as x goes from 1 to 3. So that becomes 2 pi times, let's see, 2 pi times x to the 4th over 4 minus x squared over 2, evaluated at 3 and at 1. And so we end up with this answer, 2 pi times, what is that, 3 to the 4th over 4? So that's 81 over 4 minus 9 over 2 minus 1/4 minus 1/2. And of course, I should have parentheses around all of that because 2 pi is being multiplied by all of that. So whatever that simplifies down to, that would end up being our actual area, or I should say our actual volume of this problem. So that's just a reminder that we can explicitly solve these, even though most of the time, once we get to this step here, I'm actually pretty happy. I sort of have this knowledge that we can proceed and explicitly solve it. So a lot of this, as always, is in the setup, in figuring out what R is, and figuring out what H is. To that end, problem 3 is almost identical to problem 2. We have the same x and y values that we're creating here. The main difference is the line or the axis of rotation, the axis of revolution. So take about 3 or 4 minutes, try to set up this problem, see how it changes from the previous problem. So changing that axis of revolution, how does that change our picture? And how does that ultimately change the integral? Take 2 minutes to work through that, and we'll check in 2 minutes. right, it's about 2 minutes or so. Let's check in. If you're still working, feel free to keep working. This time I won't explicitly solve the integral all the way out. I'm mostly interested in how it changes the expression that we would have to integrate. And so I'll point out, I'll try to draw basically the same picture. So, I'll forget it. Not going to ultimately be that great of a picture, but we end up with something that kind of looks like this. Poorly drawn to scale, but we have this region, same as before. And the main difference in what we're looking at here is the line on which we are integrating. And that line is, or I'm sorry, the line on which we're revolving. And that is the line x equals -1. That is this line right over here. I'll draw in a different color to emphasize it. So the line has changed. It is now the line x equals -1 that we're revolving around. And what we see if we go to construct our cylinder is that for a given x value, I'll draw just about the same x value right here. For a given x value, the height of the cylinder has not changed. The radius of the cylinder has, right? We've ended up with a slightly wider cylindrical radius here. And so what we see is that in this case, we're going to end up trying to set up an integral. Again, it is going to be an integral involving x values because we're indexing our cylinders according to the x slice that we're using to create the cylinder. So this is an integral as x goes from the leftmost x value to the rightmost x value. So again, that's going to be from 1 to 3. And then we have our 2 pi. We have the radius, which has changed now. So at our given x value, let's take a look at this. For our given x value, the radius goes all the way from x down to the axis of revolution. And so in this case, that total distance, that r of x, is going to be x plus 1. We could potentially write that r of x. We can either see that visually by noticing that the radius, actually I'll zoom in here so we can see this. The radius is going to be this distance. So here's our y-axis. It's going to be this distance, which is x, plus this distance, which is 1. And so the total radius is just x plus 1, that entire distance right there. Or we could use the formula from up above that said it was x minus the axis of rotation. In this case, x minus -1 also gets us x plus 1. So what we see here is that we get 2 pi times this new radius. This new radius is x plus 1. And then the new height, right? The new height is the same as the old height, right? It went from, at our x value, it went from this y function, so y equals x squared, down to this y function, y equals 1. So we ended up getting x squared minus 1. And we'll stop there, but notice we could explicitly compute this. We would have to do the same distribution thing. This time we'd have to FOIL, and then we could explicitly compute this. I think looking at these two problems side by side and noticing sort of the subtle difference between them is really valuable. So I do want to pause here to see if anybody has any questions or anything that we should talk about further. In particular, changing the axis of rotation didn't change the bounds of integration, right? We were still integrating from this x value, still integrating from this x value here up to this x value here. So x equals 1 to 3. We are still taking an arbitrary, just calling it x, an arbitrary x in there. The height at that x was the same. It was just the radius that changed. Yeah, absolutely. I'd be really happy to. So the question was, can we talk, or can we just repeat why the radius is x plus 1 here? So the radius, at its core, I like to think about this geometrically, always, right? I'm geometry nut by profession, I guess. But geometrically, the radius of the cylinder, let me pull this into frame just a little more. The radius of the cylinder, notice, is going to be from the center of the cylinder, that's the center of the corresponding circle, that's this axis of revolution, out to the outer edge of the cylinder. So that's an radius for this particular cylinder. I'm calling it r of x because the radius that I've drawn depends on this outer x value that I'm currently looking at. If I chose a different x value, I'd get a different cylinder with a different radius. So that's why I call it r of x here. But specifically, for this one, we've got this radius. We have to figure out what its length is. And its length is going to be just the distance from this x value up to this x value. And now I realize that's slightly confusing because this x value I'm just naming x. It's arbitrary because it's arbitrary, yeah. But this x value is specifically the x value of -1. And so this distance is equivalent to the distance between an arbitrary x value and -1. And our distance formula says, that this is the distance between x equals -1 and x equals arbitrary x is going to be the absolute value of x minus -1, aka x plus 1. We can also see this visually, and this is actually how I first saw it, as this distance that I've drawn up here is going to equal this distance, which is just x, plus this additional distance, and that distance has a total length of 1. So that's a different way that we could see that the total distance is x plus 1. Now you might actually note something here, and this mirrors, or this follows a conversation that we had last class, similarly talking about radii, in which when we broke it down, we realized that the distance formula secretly has this absolute value in it, which means that if we had a different picture, right? So blah, 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 different picture over here, different region that we're interested in. Let's pretend this is our region that we're interested in. If we had a different picture where our axis of revolution was off to the right, and this is what we were revolving around, we'd actually have to be a little careful how we defined our radius, right? Our radius in this case would be from our given x value up to the axis of revolution. And so for a given x value, let's call this arbitrary x. Let's call this x equals c. It would no longer be x minus c. In this case, it would be c minus x would give us that distance. Because again, we're trying to think about the positive distance from this point to this point. That gives us the radius that would allow us to ultimately form that cylinder. So very similar to this consideration that we had last class. Last class, it didn't matter because our formula was the formula for area of a circle. It was pi times that radius squared, so it didn't matter. This time it matters. And it matters because our formula is now 2 pi r. If we go through the and we accidentally have this incorrect, we'll end up with a negative answer instead of the positive answer that we want, right? Our volume should always be positive. So there is an interesting wrinkle, let's say, an interesting wrinkle to this problem. And I guess how we set up the radius. All right, I love it. That was a great question and a great little side conversation. Any other questions about this? Like no questions out there in the virtual world either. Okay, great. let's see. So I want to talk about at least one more of these problems. I don't actually know if I care which one, but I also want to have this conversation about, oops. I want to have this conversation about the disk versus the washer method. And yeah, let's pivot to problem 4 to talk about this. Problem 4 gives us a new region to consider and a new integral to set up. Let's set up this integral using the method of cylindrical shells, but let's also take some time to talk about why cylindrical shells is the best method to use in this particular case, because this will become an issue for us. Looking at a problem and figuring out whether we want to use the washer method or whether we want to use, I should say the disk or washer method, or whether we want to use cylindrical shells. Okay, so let's take a look. The function that we are integrating, or I should say the area that we are revolving, is the solid region bounded by y equals this function and y equals 0. So what does this look like? As a side note, this is also a lot of fun because we get to remember how to figure out what different functions look like, which is not always easy. So y equals 0, that is just our x-axis. That's not so bad. That's y equals 0. The other function is y equals x times x minus 1 squared. And there's some question about how we know what that looks like. So here's my argument to figure out what this looks like. First, I'm going to point out that this is a cubic function, right? And it's a cubic function because there's an x cubed sort of hidden in there. If we were to FOIL out the x minus 1 squared, we'd have an x squared, and then we multiply by x. So there is an x cubed sort of hidden under the surface. So a cubic function, at least kind of looks like this. Maybe it looks like this, but it has that squiggle shape to it. And in this case, we can observe that the x-intercepts, right, the places where this function equals a height of 0, they occur at x equals 0, that's from this first piece, and x equals 1, that's from this second piece. Right, so we know that it's going to cross the x-intercept, or it's going to cross the x-axis twice, at x equals 0 and at x equals 1. Finally, we can do some more detailed analysis to figure this out, or to remember that this is true. But because the x minus 1 is squared, that means that at x equals 1, this locally looks like a parabola. So it kind of looks like that because of that squared piece. So this gives us enough to cobble together this image of x times x minus 1 squared. Realize that it kind of looks like this. It's this cubic function, so it kind of has this shape. And specifically, it has that parabola shape at x equals 1, so it sort of bounces off like this. And once we've identified that, we can identify that the region we're interested in, the only finite bounded region, is this region right here. So we want to revolve this region around the y-axis. So we want to revolve it around this. Again, I'll point out, before we jump immediately to cylindrical shells, I'll point out that there's two ways that we could go about doing this. One would be to create a flat line like this, revolve that, and that would give us this disc. I guess technically this washer, because we can stick our arm through it. But it would give us this washer, and we could then try to approach this using the method of washers, using that formula. Or we could do this method, taking a vertical line, revolving it to create this cylindrical shell, which I'm going to redraw because that was terrible. But getting a cylindrical shell that kind of looks like this. Now, we're ultimately going to see, in this case, we would prefer to do cylindrical shells, but it does beg the question, why would we know that we'd want to use cylindrical shells in this case as opposed to discs or washers? So let's illustrate that by pointing out or by showing how easy the formula for cylindrical shells is here. And then we'll turn around and show how hard it would be to calculate the formula for disks and washers. So first we have our cylindrical shell. At this point, we're getting pretty good at not only drawing these things, but also in coming up with the right formula to describe them. The method of cylindrical shells would then suggest that at a given x value, right, like this x value right here, we would have a formula. This would be x goes from something to something. We have the radius at x. And notice the radius at this point is just going to be that distance there. That's just x itself. So we get r of x equals x. And then the height is given by this height right here. That's the height from the y-axis up to the function. And so that's just given by h of x equals x times x minus 1 squared. Right? It's the height from that down to 0. And then we can realize that our x values range from 0 up to 1. And we basically have all of the ingredients we need to set up the appropriate integral. We now have the integral as x goes from 0 up to 1 of 2 pi times r of x times h of x. And we're happy. At this point, again, I have said it before and I'll say it again. At this point, we could go on to actually figure out what this integral is. We would get an answer. It would be fine. We're all really good at that. And the challenging part is part up to here. So I want to stop here, right? We've set up the integral. So we've done the fun stuff / the hard stuff. Now, and what we see is that our formula was not that bad. Now, if we wanted to use the washer method instead, let's see how challenging that would be. And I'll zoom in down here to do this. So if we wanted to use washers, we have our same picture. So it kind of looks like this. Kind of looks like that. It's this region here. But remember, the setup for washers was as follows. We made slices that were perpendicular to the axis of revolution, like this. And then we had to figure out, I guess, in the revolution piece, here's this revolution piece. If we took this disk and we just sort of looked at it off to the side, let's look at it. Let's look at it off to the other side. We would have to figure out what the big R was, that big radius, and what the little r was, what that little radius was. And so we would have to integrate then. I would say each of these radii, notice, should be functions of y because they change with respect to y. So a different y value, a different sort of point of slicing, different y value would give us a different outer radius and a different inner radius. And so we would have to set up an integral in which we had the integral as y goes from something to something of pi times that big R of y squared minus pi times that little r of y squared. And then the question is, what are these somethings, right? We have these bounds of integration and we have these radius functions that we have to figure out. And the catchphrase or the point is this. This is challenging. I don't actually have a great strategy for figuring this out. I know, maybe I should say, I know that the bottom y value is y equals 0. Check. What is this, though? What is this top point? Right? It's from y equals 0 to y equals question mark. So we would have to figure that out, and that seems challenging. And then we would have to figure out these radii. And remember, the way that we did that, if it was a function of y, we have y equals x times x minus 1 squared. We would have to turn this into a function x equals blah, 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 a bunch of stuff involving y. We would have to do that and figure out which x expression corresponded to the outer radius and which corresponded to the inner radius. So is this possible? Yes, theoretically. Is it enjoyable? Probably not. Is it challenging? Definitely. So in this case, we can set up the integral, just like we set up the integral for cylindrical shells. But when it comes time to actually fill in the pieces, figure out what big R is, figure out what little r is, figure out what the bounds of integration are, it is much more challenging than in the previous example where r of x and h of x were given to us so immediately. So that, even though the method of cylindrical shells feels slightly less intuitive, in this case, actually figuring out what to plug in is so much easier. So this, unfortunately, gets the frowny face, being kind of challenging. Okay, I want to zoom out so that we can see all of these together, and I do want to pause to see if there are any anything that you'd like to talk more about in either of these problems. Any questions, any comments, any concerns? All right. So, pivot down here. No, there's a few different problems. Let's take a look at problem 6. I'm going to skip problem 5. I'm just keeping an eye on the time. I think problem 5 would be similar to others that we've tried. Problem 6 asks us to set up an integral in both ways. So set up the integral below using both the disk/washer method and the shell method. So this is a great example of seeing how we can look at the same problem through two different viewpoints. And let's see if we can figure this out. All right. So set up the integral using both the disk and washer method and also the shell method. We're looking to find a revolved region about the y-axis, and the region we're revolving are the curves x equals y minus 1 squared and y equals x minus 1. Okay, so the first thing we have to do is figure out what this region even looks like. And this is kind of weird, right? This is sort of written in a non-standard form. Normally we write our equations y equals a function of x. Here this is written implicitly, and specifically it's written x as a function of y. So maybe just off on our scrap paper, for today, our scrap paper is going to be the area right above this. Off on our scrap paper, we can remember that y equals x minus 1 squared is going to be this parabola, right? This usual parabola, y equals x minus 1 squared looks like that. And so x equals y minus 1 squared will be the same thing, just tilted sideways. So it has its vertex at a height of 1. And it looks like this. Right, so there's nothing too deep going on here, but it is written in a sort of non-standard form, so I wanted to remind us all about that, right? Sort of flipping the role of x and y gets us an expression that looks like this. I might come back to the scrap paper in a little bit to dissect that further, but for the moment, we've just identified what our first curve is. It is this sideways parabola, and we know it's sideways because it's written x as a function of y. So what we have then, back here on our real paper, okay, there we go. So we've got our sideways parabola, kind of looks like this. And then we've got the line y equals x minus 1. This is just a line. It has a slope of 1. It has an intercept of -1. So it's going like this. And notice, this will intersect our sideways parabola. First of all, it'll intersect it at this point right here, the point 1, 0. And then it keeps going. And it intersects it up here. We got to figure out what that point is. So this point is the point 1, 0. And let's think about this. We could set these equal to each other and then solve. Is that the best way to do this? It's a fine way to do it. Let's do it. So we could set these equal to each other and solve. Maybe I'll go back up to my scratch paper for this. The question is, what is that point? We are looking for the point where x equals y minus 1 squared and y equals x minus 1 are equal to each other. But y equals x minus 1, that can be written as x equals -1 minus y. Nope, that's a lie. That's a lie. X equals y plus 1, right? Just adding the 1 to the other side. And so what we get then is we're looking for the point where y minus 1 squared equals y plus 1. And then we're going to do some algebra, and it won't actually be that much fun. That's a lie. It's going to be pretty fun. So we're going to have this. We get y squared minus 3y plus 1 minus 1, so plus 0 equals 0. And that means that y times y minus 3 equals 0. So we have our two solutions. We have our solution at y equals 0, and we have our solution at y equals 3. And so with that in mind, let's see if we can keep this all in frame. There we go. With that in mind, notice this first point corresponded to y equals 0. That was the point down here at the bottom. That was our first point of intersection, y equals 0. That means that this point up here is our point of intersection corresponding to y equals 3. And we can recognize that when y equals 3, that means that x minus 1 is equal to 3. That means that x is equal to 4. So this is the point 4, 3. Quick sanity check. 4 equals 3 minus 1 squared. That's correct. 3 equals 4 minus 1. That's also correct. Okay, great. So we've got our 2 points of intersection. The region that we're super interested in then is this region S in between the two. So that's going to be this little wedge in here. And we're interested in revolving it about the y-axis. We're going to be interested in this region. And we're revolving it around the y-axis. All right, that was a tremendous amount of setup, but this is great. We're in a good place now. Our goal again is to try to do this using both the disk method and the washer method. And in doing so, we'll try to figure out which one is easier. Let's do the disk/washer method first. because it's been a little bit since we've explicitly solved one of those out. The disk/washer method would draw a line perpendicular to the axis of rotation. That's going to be right here. And then as it revolved, it would sweep out this washer. Right? It would sweep out this washer. And our goal is to integrate up the area of the washer. Now, the washer depended on the y value, right? That was what gave us this slice that we revolved. So the washer method, the disk/washer method, would give us an integral involving y values. So it would be the integral as y try that again. Nope, that is not what we wanted to do. Let's try that again. All right, so the disk washer method, we have an integral as y goes from its leftmost y value, or its lowermost y value, up to its uppermost y value. And that is explicitly y goes from 0 up to 3 of pi times the big radius squared minus pi times the little radius squared. All right, and so the big radius is just given by, and let's confirm, the big radius is just given by going from the y-axis up to that straight line. Right, that is the larger of the two radii. That is going up to the line y equals x minus 1, but our integral is in terms of y's, so we have to write our x value as a function of y. So we're going to convert that into the other form, x equals y plus 1. And that's our bigger radius. So we get pi times that bigger radius, y plus 1 squared, because that is the x value corresponding to the y, and then minus pi times our smaller radius squared. And our smaller radius is going to be this tiny distance here drawn in red, right? Specifically from the y-axis up to this sideways parabola. And luckily for us, that's already given in this nice form. So that's from pi times smaller radius is y minus 1 squared. And then we're going to further square it. All right, and let's leave that there. Man, we don't actually want to compute that integral, but we have set up this disk/washer method appropriately. Let's see. In the few minutes we have left, let's at least begin setting up the shell method. We got our same picture, which I'm just going to copy down here quickly. Curve that looks like this. Got a curve that looks like this, in which we can pretend that line is straight. And so what we end up with is still this region revolved around the y-axis. But this time we are constructing these shells. Right, we're taking lines that are parallel to the axis of revolution, and we are constructing these cylindrical shells as a result. All right, so our formula for shells is very similar. Maybe first of all, I should say, notice these shells are indexed by their x value, and different x values will give us different shells. And so we want to integrate as x goes from its leftmost point to its rightmost point. And in this case, that's going from 0 up to 4 of 2 pi times the radius times the height. Now, what we see is that as we go through this, first of all, the radius is just going to be from this axis of revolution, that's x equals 0, up to our arbitrary x value that we're interested in. So our r of x is just equal to x. But the h of x is going to be where we run into trouble, right? What is the height of this cylinder? Well, as drawn, the height of the cylinder is going from this parabola down to this straight line. And in order to figure out the equation of the parabola, we would have to go back up here and solve for y. Right? So h of x is complicated, but it gets worse. It gets even worse. Why does it get worse? It's because we can't, well, first of all, yes, we have to subtract the top from the bottom, but then, maybe this is what you meant, after we hit this point, if our x value is small enough, it's no longer parabola minus straight line. It becomes 1/2 of the parabola minus the second half of the parabola, and that will give us our height. So in fact, the height changes its behavior here at x equals 1. So not only is the height complicated, I'm going to say the height is really complicated. And so this is an example where we could set this up using the shell method, but we'd be much happier setting it up using the disc or washer method. Okay, and we're definitely at time, so I do want to stop there, though I'll stick around for a minute if you all have any questions. Yeah, thanks so much. It is always great to see you all. So happy Wednesday morning to you. And yeah, I guess take care. Have a great rest of your week. I will see you all on Friday. Thanks, Elijah. Thanks, Audrey. See ya.